I'd like to introduce you to this webinar on soil health and compost and some innovative strategies for soil amendment, erosion control, and stormwater management. We have two participants today, Geoff Kuter from Agresource and Britt from Filtrexx. Geoff will start off the presentation and then we'll shift over to Britt, and then we'll have some time at the end for some questions and answers. I am Mark Companion, and I'll be managing the chat section. So if you have any questions near the end of Geoff's presentation, send them to me, and then we'll have Geoff answer a couple of questions. So without further ado, I'll hand it over to Geoff.
Okay, thank you very much. Welcome everybody to this presentation. Just as a way of brief introduction, I'm with Agresource. We're a Massachusetts company engaged in making compost, distributing compost, and in manufacturing soil mixes and manufactured soils with compost as a significant ingredient. I got involved in this composting industry back in the early 1980s when I was doing postdoctoral research at the Ohio State University, Ohio Agricultural Research and Development Center in Worcester, Ohio. In my presentation, I'm going to briefly talk about some of the benefits of using compost, how compost can be used in projects where we're designing systems to treat stormwater, and then talk at the end about the issues with phosphorus. One of the things that's most notable about using compost is when we use compost as a soil amendment, we have impacts on soil physical properties, soil chemical properties, and soil biological properties, and all of these are interrelated. We can't change one without changing the other. These changes to soil properties have direct impacts on soil quality, which in turn affects plant health and our environmental health. Again, all of these interactions are highly linked. So for example, typically when we're looking at stormwater projects, we're looking at ways in which we change soil physical properties. When we add compost, we increase soil water holding capacity, we improve the physical structure of the soil, for example, increase soil aggregation and pore space, and we lower the soil bulk density to make a lighter weight soil. When we do these, we reduce the amount of water we need for irrigation to grow plants. We improve the ability of water to infiltrate into the soil surface, which in turn reduces water runoff and erosion, and we create a much better rooting environment. So in summary, when we look at environmental benefits from using compost, we see that compost amendments increase water infiltration, reducing a runoff, compost improving physical structures of soils, particularly the creation of macropores, and we improve plant root growth, which promotes in turn more rapid uptake of water, uptake of soluble macronutrients and micronutrients, and reduces leaching potential. We also then increase the cation exchange properties of soil, which improves the retention of nutrients. And then lastly, the carbon in our compost is retained in the soil. So all of those are simultaneous impacts that we get when we add compost. Now, when using compost in any particular project, it's important to realize that not all composts are the same. Each compost is going to be a little bit different depending on the feedstocks, how it is processed or made, the age of the compost, all of these which will impact the nutrient content, nutrient availability, and compost stability. For example, when we make compost from manures and biosolids, these typically are going to have higher concentration of nutrients such as nitrogen, phosphorus, potassium than when we make compost strictly from leaves and yard debris or woody plant material. The duration of composting and how well we cure or how long we cure the compost may reduce the quantity and the form of the organic matter and result in increasing stability. The organic matter that is left behind will be less subject to rapid degradation In other words, the material will last longer in the soil. We also see the compost different in their microbial populations. We know that compost microbial populations can be important in suppressing plant disease, but again, the microbial activity is also going to be influenced by the amount of carbon that's available in the compost and this particular soil environment in which the compost is added. So when we look at using compost, typically we find, it's easy to get caught up into the details, but typically we find that almost all soils are going to benefit from some addition of some kind of compost, but the type and the rate of compost application that we use is going to be determined by our project goals, our existing site, and soil condition. Thus then, when looking at using compost, particularly in stormwater or environmental remediation type projects, it's critical that we test the compost and we test the soil using appropriate test methods. We've been involved in Agresource in manufacturing soils and providing compost for a number of projects that were designed for stormwater treatment. Typically in these projects, which are infiltration basins or sometimes called rain gardens, the soils are designed to function to allow the very rapid infiltration of water coming off paved areas or roadways. The soils then are designed to function to filter contaminants, remove nutrients, while at the same time supporting plant growth. Some of these projects, the one on our left-hand side, for example, this is under construction, a mass highway project. The water coming off the roadway goes into this basin and infiltrates back into groundwater. The center and right-hand pictures, these are examples of rain gardens or infiltration basins constructed to take water off parking lots at shopping centers. These are designed to have a vegetative landscape component. They have to also look good. So it's important then that we have a soil that will not only filter the nutrients and contaminants, but will also support plant growth. We've also been involved in a number of wetland remediation type projects. This particular project here shown in these sequence of pictures is from the University of Hartford in Hartford, Connecticut. These are this particular case, we're building a wetland, a soil with a very high organic content designed to hold and retain the water that's coming off the pavement, the parking lot area. And we have plants that are adapted to tolerate a flooded soil, a high organic, a high water soil content. In contrast to our rain gardens, where we have plants that are going to be subjected to intermittent flooding and intermittent drought. One of the issues that we see, particularly when we're using composts in treating stormwater or in wetlands or in projects where we have compost directly next to our water resources, or the runoff from that composted area is going into a lake or river, is phosphorus. And the issue we have to address is compost phosphorus using compost. Are we part of the problem? Are we contributing phosphorus in a negative way, or are we part of the solution? The key then is understanding how we can use compost without risking phosphorus contamination of our water resources. When we look at composts and we look at phosphorus in particular, we find that composts vary tremendously in the amount of total phosphorus that we have. Typically, compost made from strictly leaves and yard waste, we get a lot of this in Massachusetts, is going to be relatively low in total phosphorus compared to a biosolids compost or a manure-based compost. Here we have data on total P2O5 pounds per cubic yard for leaf and yard waste and two different biosolids composts. And we can see with the biosolids composts are almost a 10-fold higher total phosphorus. But we also see, if we measure the amount of water extractable or phosphorus that is readily water soluble, it's a relatively small percentage of the total phosphorus. And in the case of the two biosolids composts, we see a huge difference. The one biosolids, where we have a biological phosphorus removal plant, 13% of the total phosphorus is water extractable. In contrast, the other compost, where we have chemical phosphorus removal being used at the wastewater treatment plant, we see less than 2% of the total phosphorus is water extractable. Thus, when we look at the water extractable P2O5 pounds per cubic yard, we see that there may not be all that much difference between some of the biosolids composts and the leaf and yard waste compost. Now, food waste compost, manure-based compost may be somewhere in between these variables. We see different sources of organic matter are going to have very different levels of total phosphorus and very different levels of water soluble. This is a table from Dr. Amy Schober, University of Delaware. She looked at various biosolids products, composted, uncomposted, heat-treated pellets, etc. She looked at various manures, and she looked at triple superphosphate, and she looked at the percentage of the phosphorus in these products that were water soluble. And you can see, in general, the biosolids products, high total phosphorus, but very low percentage of water soluble phosphorus compared to the manures here, which have a very relatively high percentage of total phosphorus that is water soluble. Being water soluble, when we use those products, this material can readily leach off. And we see, though, in compared to triple superphosphate, where approximately 85% of the total phosphorus is, again, readily water soluble, readily going to leach immediately after these products are added to the soil. Again, food waste composts mixed with yard waste are going to be somewhere here in the middle of this graph. What are the risks when we use compost to water? When we look at actual research studies with compost, we see there's actually a relatively limited number of studies that have been done. Here I point out three that show some of the variation of data that we get. One of the most interesting studies was done by John Spargo and others down in Virginia. They looked at adding compost to agricultural soils, and they measured phosphorus in the runoff coming from these compost amended plots. And here they found that the amount of phosphorus that was lost in the runoff was actually much lower where they used the compost amendments, simply because they resulted in less volume of runoff. The concentration of phosphorus went up, but the volume of runoff went down significantly. Thus, the amount of phosphorus coming off the compost amended plots was much reduced. So again, the physical improvements to the soil properties outweighed the potentially negative effects of adding additional phosphorus in these plots. Other studies with turf, a study by Johnson et al., also back in 2006, they found using dairy manure composts no increased losses of phosphorus from runoff and in the soil below the root zone compared to where they used no compost. However, other studies like Easton and Petrovic's study earlier, they also looking at turf plots found in the first year there was significantly increased phosphorus leaching and runoff where they use compost in compared to no application of compost or just compared to fertilizer. By the second year, once the turf had been fully established, there were no differences. The compost did not increase the amount of phosphorus lost from these plots. And their results generally support the argument we've seen over and over and over again. Where we have bare soil, we're going to see losses of phosphorus primarily from runoff. So when we use compost, the faster we can get an establishment of a dense plant cover, of a surface cover, and of root growth, the slower we will have nutrient loss, both phosphorus and nitrogen, from that plot. So again, these are interrelated impacts. Establishing rapid cover, good root growth, good dense turf cover will reduce runoff and leaching, even though we're adding phosphorus to the soil. In looking at this whole issue, we want to look at again, how we can use test data to support the work we're doing when we add compost as a soil amendment. Soil test methods that we typically use at the university test labs are going to give us soil extractable phosphorus, which is used as a measure to look at a plant available phosphorus in the soil. In other words, we use that test data to determine the response to added phosphorus to the soil. These soil tests and results then are by themselves not good predictors of how much phosphorus is going to be lost through either leaching or runoff. They're going to tell us whether if we add additional phosphorus, we will see improved plant growth response. If we want to look at a predictor of leaching of phosphorus from soils, how much phosphorus will be lost, it's best to look at a phosphorus saturation index. This is a measurement of the molar ratio of phosphorus over the amount of iron and aluminum in the soil using an oxalate or a Mehlich 3 type extraction versus the Morgan extraction that the typical agricultural soil test labs are going to use. When we drive this number low, when we increase the amount of iron and aluminum in relationship to the phosphorus, the amount of water-soluble phosphorus will be very, very low, and we can actually create a soil mix in which soluble phosphorus will be absorbed and retained. So if we push that PSI level below 0.1, we can actually create a soil which will absorb water-soluble phosphorus in our stormwater or in our rainwater and hold that in the soil matrix. One way we can do this, and this was discussed at some length by Dr. Eric Roy's webinar, is by using things like water treatment residuals, which are high in iron and aluminum. These can be used as soil amendments with their compost, reducing the PSI and reducing the potential leaching of phosphorus. Again, we need to look not just at total phosphorus, but at the water-soluble phosphorus and the iron and aluminum phosphorus interactions. It's also, though, however, important to remember, phosphorus is not just going to be bound to iron and aluminum, but it will also be bound to calcium in the soil. So with calcareous soils or soils with high calcium contents, we can have the same impact. We can hold the water-soluble phosphorus in the soil and prevent it from leaching. Of course, the PSI is not going to tell you anything about the calcium way in which calcium interacts. Thus, in conclusion, when we look at using composts, we want to look at how we can use them effectively to improve soil properties. And we know that by raising soil organic matter, we can reduce runoff and erosion, reduce the negative effects of nutrients ending up in our surface waters, our lakes, our ponds, our streams. Compost will inevitably increase levels of soil phosphorus. Thus, we have the potential whenever we use compost for leaching of phosphorus, particularly when we're adding compost to a very sandy soil and before we get the establishment of that dense root mat and dense plant growth. Leaching, the amount of phosphorus that is actually leached, is going to be highly dependent on the soil chemistry. Thus, measurements of water extractable phosphorus and using the phosphorus saturation index can be done to evaluate our risk. Looking at the total amount of phosphorus in our compost really tells us almost nothing. Instead, we need to look at how phosphorus is interacting with other chemicals, aluminum, phosphorus, calcium, in the soil. When we do repeated applications of compost to provide nutrients, such as nitrogen, This may not be justified when we have areas where we're particularly sensitive to peat losses, because as we apply compost every year for nitrogen, we're going to be adding excessive amounts of phosphorus into the soil. And that's, unless we do have a very low PSI, it is very difficult to retain that phosphorus in the soil mix. One way I've looked at evaluating this and interpreting this is, okay, when do we use compost and how do we use it? Well, first thing we want to do is test our existing soil. We want to test it for phosphorus, and we want to test it for soil organic matter. We have when we do those two tests, we're going to have 4 different options. We're going to have soils that are below optimal for phosphorus and low in organic matter. In these cases, clearly using compost to reach an adequate organic matter, to improve water infiltration, to reduce runoff, to reduce our fertilizer use, this is clearly a green light. Where we have cases where we have high levels of soil organic matter or adequate soil organic matter and above optimum levels of phosphorus, that quadrant, or lower right-hand quadrant, we don't want to use compost. There's no justification for adding additional organic matter. And in those particular cases, we want to eliminate further uses of phosphorus. Where we have, again, adequate levels of organic matter, even if we have low levels of soil phosphorus, there is no reason to continue to apply compost again and again. Adding additional organic matter is unlikely to have any additional benefit on environmental or soil health. We have one set of conditions where we really have sort of kind of a yellow light. Here where we already have adequate or optimal soil phosphorus levels and low organic matter. Here, the addition of organic matter is going to clearly have the potential to reduce runoff, reduce erosion, reduce the loss of phosphorus, but we have the potential that because we already have adequate phosphorus in the soil, that we can have leaching of phosphorus into our groundwater and ending up in our surface waters. Here we want to be careful and look specifically at risk factors. Is this a critical zone? Are there mitigating circumstances here that would call for the added benefits of using compost, and where we can be comfortable that we will not have risk of phosphorus? Here's where we want to look at using phosphorus compost, which have very low water extractable phosphorus levels. That's pretty much the end of my presentation.
Thank you, Geoff, very much. I think we'll shift over to Britt's presentation just in the essence of time.
Thank you. Just a quick introduction about myself. I'm an ecosystem scientist and research and technical services director for Filtrexx International. Filtrexx is arguably the largest end user of compost in North America. Definitely so for erosion and sediment control and stormwater applications, which is really our core business. We don't make any compost. We just utilize it with our technology and our applications, some of which I'll be talking about as an overview here. I did my doctorate work at the University of Georgia in the Odom School of Ecology, where I researched compost-based best management practices in the stormwater application. I was an adjunct professor at the School of Environmental Design, also at the University of Georgia, and also worked in the engineering department there for 6 years as a research and outreach engineer and a state specialist for stormwater management, organics recycling, and pollution prevention efforts. With that, in the interest of time, I'll jump right in here. Just a real brief outline of how we'll move through the next 20 minutes or so, 15, 20 minutes or so. I'm gonna talk briefly about, just to lay a foundation of stormwater management, really moving from gray to green infrastructure. I'm gonna talk about how compost how we're using compost in the stormwater context. I won't talk about it in a vegetation context. I think everybody is probably familiar with that, how compost can be great for vegetation establishment and plant sustainability, but I will talk about how it's being used both for volumetric reduction of stormwater and also biofiltration. I'll talk about some of the key compost based best management practices, some of the key research, particularly as it relates to the performance of these practices. I'm going to share a case study with you at the end, which I think kind of pulls some of this stuff together. If you've seen me speak before, you've probably seen some version of this slide. It does a great job of graphically depicting what happens when we change our land use patterns from natural watersheds and landscapes to greater development and urbanization. And oftentimes I'll sort of update this slide depending on what we're going to talk about. But what the core of this shows you as you move from these natural systems like you see on the left to greater development and urbanization, you'll see a lot of, in the natural systems, you'll see a lot of biomass, you'll see a lot of vegetation, you'll see organic matter, you'll see grasses and trees and multi-story vegetation, the interactions of above ground and below ground ecosystems. And what happens is it creates a very tight hydrologic cycle to the point where there's very little stormwater. And because there's very little stormwater, there is very little pollution, and very little pollution, if any, that's transporting or migrating to surface water bodies. And you can see as you get rid of, as you trade that for development and urbanization, that red sort of creeps in, and you get rid of what some folks would call natural capital, like you see on the left. And you get more and more impervious surface, as well as soil disturbance with greater runoff. We know there's lots of studies now that show the more stormwater you have, the higher the pollutant loading is within that stormwater. And of course, the more stormwater and the higher the pollutant load, the more of that gets into receiving water bodies, leading to greater water quality impairment. So quite literally, the idea of green infrastructure is really to get that biomass and these natural systems like you see on the left, and to design and implement them into the urban environment. But there's another way to look at it, which people are beginning to talk more and more about. Ecosystem scientists have been talking about this for quite some time. But if you look at the natural systems on your left, often referred to as protecting or reestablishing or conserving natural capital in the form of these natural systems, one thing that the natural capital does for us is it gives us an ecosystem service for free. In this case, it's giving us stormwater management for free. It's managing the hydrologic or the water cycle for us for free, to the point where we don't really have to pay for stormwater management under these scenarios. But when we get rid of that natural capital, the ecosystem service is decreased, and actually now we have to really pay for it in real dollar terms. And so you can now look at that red as actually being in the red. We have to pay in real financial terms to manage that stormwater, whether it's build containment systems, conveyance systems, or treatment systems, real infrastructure in order to handle that. That really takes a viewpoint on the watershed scale. This really takes you down to the site scale, which is where most of us as professionals are working. And the reason why I want to take you down to the site scale is not just because this is where most of us can have the greatest impact in our professional decision making and in our everyday lives. You begin to see really the components of what happens in the landscape here. And you look at the hydrologic values here, and they're very similar to what they are on the watershed scale. But you'll notice here layers of organic matter. You'll notice in what that helps to provide. It's minimizing stormwater runoff. You'll also notice that the arrow pointing down, 35% surface water detained or infiltrated. What happens in this process is when runoff moves down through the soil profile, organic matter and topsoil profile, a couple of things happen. It may get absorbed there and become plant available. It may move just below the soil profile, what we call subsurface or interflow, actually getting naturally filtered in that process before it recharges a surface water body, or it may go down deeper and recharge aquifers and groundwater, also getting filtered as well. And it's really these concepts that lend credence to why we want to rebuild and put organic matter back into the landscapes in a responsible way is really to mimic what we see here. So here's a list of compost-based best management practices that all use compost in whole or in part. These are all generic terms that are often utilized in both construction activity stormwater management, you see on the left, and post-construction stormwater management, like you see on the right. Generally speaking, at least at Filtrexx, we use one of two types of compost for all of these applications. And they're graphically depicted here. The one on the left is what we call filtration media. Sometimes we call it a biofiltration media. The one on the right is generally used for growing media and erosion control. So the one on the left is really designed specifically for passive filtration of stormwater. We want water to actually move through these systems, but trap not only sediment, but also soluble pollutants and present in the stormwater as well. And then on the right, what we're trying to do is not only establish vegetation, but we want to absorb rainfall, thereby minimizing runoff. We also want to slow it down as well. So if you're looking at both of these types of media and you're thinking to yourself, God, neither one of these look like compost. Ding, ding, ding. That's actually a key take-home message. We're not using what a lot of folks would consider to be a fine grade compost or something that resembles a coffee ground type compost. We find that in our applications, although that may be considered high quality compost for some applications, we would consider them low quality compost for the applications that we're utilizing. So consequently, and you can, some of this piggybacks on what Geoff was saying, but we're generally only using yard waste and green waste type compost here. So by doing that, we're already selecting out high phosphorus, high nutrient type compost. We're also self-selecting by removing some of the fine particles as well that would thereby contribute to some of the potential phosphorus issues. And you see that visually when you look at these. If you can remove that, and this actually piggybacks on some of the PSI, phosphorus saturation index that Geoff mentioned, you can take a compost from being a potential source to a potential sink. And that's actually what we're seeing here. And I'll show you some data here in a minute. One last word about the erosion control media. Well, one of the things we're doing here is we're actually designing a BMP, another BMP actually into the media. We're actually designing surface roughness into the media itself. Surface roughness is actually a BMP itself in both erosion control and in stormwater design context. And we do that by selecting larger particle sizes. So we want to have some small particles in there to help absorb rainfall, to help anchor and to grow vegetation, but we want these larger particles in there also to slow down runoff when we do get runoff occurring. It makes it less erosive, it makes it less destructive, makes infiltration more likely to occur. And actually you may be thinking to yourself, wow, this actually looks more like a forest duff layer or a forest floor than it does a compost. And if you're thinking that is also true. That's actually by design. Some of the key research I wanted to share with you are, this is research from the University of Georgia, published in the Journal of Stormwater Conservation, that shows the ability of compost to absorb an immense amount of rainfall. This is on average, absorbing 84% of a 4-inch rain event. These are 4 different university studies that are all showing this in large scale field test plots. 2 from the University of Georgia, 1 from the University of Connecticut, 1 from Iowa State University, showing roughly 50%, 90% volumetric reduction of stormwater. This really comes into play of not just reducing stormwater, but as I mentioned earlier, when you reduce stormwater, you also reduce pollutant loading as well. And if you look at 4 different studies here, from top to bottom, 1 from Texas A&M University, 2 from the University of Georgia, 1 from Iowa State University, showing the ability to reduce nutrients, including phosphorus, to a large extent because of its ability to greatly reduce stormwater runoff, thereby reducing the overall pollutant load. And you can see in each one of these field studies what they compared the compost to, whether it's seed and fertilizer, hydromulch, or even just seed and topsoil where no nutrients were added. Let's talk about filter media for a second, and here's some applications that you can see, typical applications we see from biofiltration, bioretention, bioswale, and compost filter sock applications. This is some research done by the USDA Agresource Service to quantify the biofiltration benefits or aspects of this type of compost-based media, and the results have been published jointly in the Journal of Environmental Quality and the Journal of Stormwater Conservation. Other than the TSS and their turbidity, these are soluble forms of these nutrients that are being removed by the compost media. And you can see here when you design and you select the compost appropriately, you can remove to a great extent a wide variety of these pollutants rather than becoming a source. The metals here the metals they looked at in this context were copper, cadmium, chromium, nickel, lead, and zinc. So you're beginning to think to yourself, wow, you can use compost if designed appropriately across an entire site and in a wide variety of applications, whether in mixes or in true applications. But it's another thing to conceptualize it. It's another thing to see it in practice. This is a project I was fortunate enough to be part of, which is based in Midtown Atlanta, Georgia. It's the South Base Energy Institute, is the first LEED Platinum project in the state of Georgia. It was put in over 10 years ago. But this is probably the second largest green building nonprofit in the United States after the U.S. Green Building Council. They do a lot of training and education at this facility, a lot of testing and demonstration and certification for LEED accredited professionals. But one of the things they did is established or put in compost-based green infrastructure practices almost exclusively around the site. And you can see this in compost-based green roof system, compost blankets around the site to both for erosion control and to minimize stormwater runoff. Use compost socks to build up the walls of the bioswale and the bioretention system, which you see in the middle there. They use a compost-based bioretention media mix in the center there for when stormwater is generated and directed there. There's actually a cistern down below that captures the filtered stormwater after it goes through the compost-based bioretention media mix, and then they actually reuse that back in the landscape and for non-potable water uses within the building. So this actually is a site that captures 100% of the rainfall that falls on the site and the stormwater generated on the site. It's actually a zero discharge facility in the middle of one of America's largest cities. You can barely make out a riser pipe in the bioretention system in the middle of your screen. In the upper portion of it, by city ordinance, we were required to put that in because really nobody thought that there would be times where stormwater wouldn't need to go into the gray infrastructure. But this project is basically 10 years old, almost 10 years old. We've had several 100-year storm events, and not one drop of water has actually gone in there because of its absorptive capacity. Because they're capturing and reusing some of this rainwater and stormwater, they're actually able to offset their water usage by 84%, or about 130,000 gallons per year. Many of you may not know that Atlanta has historically been a poster child for poor stormwater management. And so several years ago, the previous mayor established a citywide green infrastructure ordinance for the city of Atlanta, making it one of the first for a city of this size, and used this as the model for the green infrastructure program. It's since been adopted by a lot of the metropolitan municipalities and counties, and since then has even expanded to the greater North Georgia region, making it arguably one of the largest green infrastructure regions within the country. So unless you're part of a program like this, you wouldn't realize when you were driving by or walking by what you're looking at now, which is what this looks like, is a high performance compost based green infrastructure zero discharge facility in one of America's largest cities. And that was fast. Thanks.
Fabulous. Thank you so much, Britt.
Yeah.
Do we have any more questions just quickly for Britt or Geoff? Okay, I have a couple of questions here. Thank you. From Emily, let's see. Geoff, in your opinion, what is the recommended adequate % organic matter?
Depends on the particular project. If you're building a lawn for home use, let's say a residential lawn that is not going to be irrigated typically you're going to want to see 5% minimum, and maybe 5 to 6, 7, 8%. If you're building a sand-based root zone for a sports field that's going to be irrigated and going to get a lot of heavy clay, 5% would be excessive. You'd be looking at the 3 to 5% range. A wetland soil is going to be 20% organic matter content typically. A rain garden soil or infiltration basin, again, you're going to be looking at the 3 to 5% organic matter in that kind of application. As I said before, a lot depends on the particular application and what you're trying to achieve in your project.
Okay, thank you. Another question, Geoff. What role do you know is involved in the fungi in the compost?
In the composting process, the high temperatures will destroy or certainly, if not outright kill, will reduce the activity of any of your mesophilic organisms. As the compost cures and cools down, typically our compost will be recolonized by mesophilic bacteria and fungi, and those fungi that colonize our compost after the high temperature phases have a variety of roles. They will continue to break down organic matter that is slow to break down, the cellulose and lignin portions, and some of those organisms that colonize our compost are actually inhibitory or even parasitic to some of our soil-borne plant pathogens. And those are considered beneficial microorganisms or beneficial fungi, and they can automatically recolonize our compost, or in some cases, compost will be inoculated with some of these organisms to promote their growth. Fungi have a number of different roles in the environment, mostly as decomposers. There are other fungi, of course, that operate as mycorrhizal associations. Most of those would not typically survive, again, the composting process, but are found in our naturally occurring soils. And there's debate on whether we really actually need to add them when we're adding, doing our planning and revegetation process.
How appropriate is using compost in establishing vegetation in roadside ditches or swales that will likely see significant flow of runoff?
I could take that. Compost, it sort of depends a little bit, like a lot of, I guess a lot of answers, but compost is often used as part of a mix in a bioswale, which is a channel or a ditch or a swale. However, when you do that, you'll want to, when you're installing it and establishing it prior to vegetation, you'll definitely want some erosion control measures that are suitable for concentrated flow. Compost by itself is not suitable for concentrated flow applications until you get the vegetation fully established. And then it depends on the rate of the flow. And there's some design guidance on the velocity of the shear stress of the flow and what type of vegetation you should use, and even whether you should use compost or not.
In response to that, I would also reiterate what Britt's saying. Quick establishment of very dense vegetative cover is always critical. The longer the soil remains exposed to runoff, the more opportunity there is for soil loss, for nutrient loss. And so you need to look at in perspective of the long-term goal of getting a vegetative cover established.
Thank you. Oh, here's one more about fungi. In your work, have you seen the use of fungi via mycelial mats in remediating runoff and in supporting riparian planting through the mycorrhizae? So mycelial mats and supporting riparian plantings through the mycorrhizae?
No, but in general, when you're talking about microbial colonization, whether it's fungal or bacterial or mycorrhizal, you need to create the right environment first. The microorganisms will typically get there, particularly if you're adding in a base soil which already has an inoculant base. Only in the cases where you're dealing with a very, very impoverished soil is it usually necessary to add a microbial inoculant. But your existing soils, unless highly abused and highly disturbed, will have an inoculant, a base population that will grow and proliferate and colonize your new soils if provided the right environment. If you add the organic matter, the microorganisms will colonize that organic matter.
Thank you, Geoff. Any last questions? Having seen none, thank you very much, everyone. I appreciate your time. If you have any more questions, feel free to send me an email, Mark Companion, and I can forward your questions to Geoff or Britt. So with that, this is the end of the webinar. I appreciate everything with you today, so have a wonderful day. Thank you. Bye.